In this video, we're going to go over section 4.6 from our textbook, which is on optimization. And the techniques used to solve optimization problems are best illustrated through some examples. So we're just going to go through several examples in this video. First, we'll look at a simple word problem here. So we want to find two numbers whose sum is 22 and whose product is a maximum. So with these word problems, it's best to kind of translate these words into mathematical symbols or equations. So there are going to be two numbers whose sum is 22. Okay. So we can call these two numbers anything we want. I'm going to say x and y. And we're saying their sum has to be 22. So x plus y is going to be equal to 22. And their product is going to be a maximum. So the product of these two numbers, so we're going to multiply them, is going to be some maximum value. And the problem becomes, we want to maximize p subject to the fact that the sum of these two numbers needs to be equal to 22. So the first step here is we want to deal with one variable. So we're going to rewrite the function that we want to maximize with just one variable. So we're going to rewrite p in terms of x. And we can do so using this equation here. Solving for y, we'll get y is equal to 22 minus x. So we can rewrite p in terms of x by plugging in our y value here into that y. And so p is going to be a function of x. And so plugging our value for y in, we'll get 22x minus x squared. Okay. And so what we want to do is we want to maximize this function here. We want to maximize this product. And so what we're going to do is use the methods that we discussed in the last section to do so. And so what we'll do is see if the second derivative test applies. Remember, if we have that the second derivative is less than 0, so negative at a critical number, then we know that we're going to have a maximum value. So the first thing we'll do is take the derivative of our function. This is going to be 22 minus 2x. Then we want to find when this guy is going to be equal to 0. We're looking for the critical number. So solving for x, we see that the critical number is x is equal to 11. So then what we want to do is take the second derivative of our function. And so the derivative, this is going to be 0, and this is going to be negative 2. And so we see that the second derivative is going to be less than 0 for all x values. So we know that we're going to have a maximum value. So when x is equal to 11, our function will have a maximum value, and in this case we're looking at the product, so have a maximum product. Alright, so what we got to do then is plug in this critical number into our function. So we'll get 242 minus 121, and so this will just be 121. So then this tells us this is going to be our maximum product. All right, but going back to the question here, we want to find two numbers whose sum is this and whose product is a maximum. And we only found one number so far, so we need to find y. And we can do so just by plugging in this x value here into y here. So we get that y is 22 minus 11, which is just going to be 11. So this tells us that the two numbers whose sum is 22 and whose product is a maximum are just going to be 11 and 11, and that maximum is in fact 121. So this tells us we can conclude that the two numbers described in the problem above are x is equal to 11 and y is equal to 11. At a real world problem here, we want to maximize an area. So we're told that a homeowner has $320 to spend on building a fence around a rectangular garden. And 3 sides of the fence will be constructed with wire fencing, which costs this much, and the 4th side will be constructed with wood fencing, which costs this much. Now, what we want to do is find the dimensions and the area of the largest possible garden that can be enclosed with this much money. So the first thing that we want to do is to draw a figure to represent this situation. So we know we're going to have a rectangular garden, so it's going to look something like this here. Okay. So I'm going to call the lengths of these guys x, and the width is going to be y here. Alright, and then we're told that 3 sides of the fence will be constructed with wire fencing. So let's just say that's these sides here. We're going to color code them. And we're also told that the 4th side will be constructed with wood fencing. So that side here. Now we know that an equation to connect these variables is going to be the area of the garden. And so that'll just be x times y. We also know that the cost to build this fence is going to be the cost of this side, plus this side, plus this side, plus this side. And then we saw from here that the cost of this side is going to be $2 per linear foot, so that's going to be 2y, since y is our linear feet. Similarly, the cost of this side is going to be 2 times x, and this side is going to be 2y. Now, since the 4th side costs $6 per linear foot, this is going to be 6 times x. So this tells us that our cost is going to be given by the following equation. We're going to say c is equal to 2y plus 2x plus another 2y plus 6x. Okay. And then simplifying this guy a little bit, we're going to end up with 8x plus 4y. All right, and so the problem becomes we want to maximize the area given or subject to the fact that we're only going to spend $320. So our cost is equal to this here. So again, our first step, like we saw in the last example, is going to be to rewrite what we want to maximize with just one variable here. So we're going to rewrite A with a single variable. And so again, we're going to use this equation here to solve for y, and then write A in terms of just x. So using this equation, we'll solve for y by subtracting 8x on both sides and then dividing this whole thing by 4. Doing that gives us 320 minus 8x over 4. So we get y is equal to 80 minus 2x. Right? And then with this information, we can rewrite A in terms of just one variable, x. All right. Now something to notice here is that we do have a restriction on x. X has to be greater than or equal to 0, right? Since remember, x is going to be the length of this rectangular fence here, and the length of the fencing can't be negative. Okay? So this also tells us that we have a restriction on y here, since y is written in terms of x. Y must also be greater than or equal to 0. This tells us 80 is going to be greater than or equal to 2x, and therefore x is going to be less than or equal to 40. All right, so now we have these restrictions. We have some restrictions on on x. So x is only defined on this interval from 0 to 40. So then our problem becomes, we want to maximize our area, which is now given by over the interval 0 to 40. Right? So we want to find the maximum value of our function a of x over this interval. And then from section 4.5, we know that since our function is going to be continuous on this interval, the absolute maximum, that is, if it exists, must then occur at a critical number or an endpoint. Right? So what we'll do is find the critical numbers. We'll take the derivative of our function here. That's going to be 80 minus 4x. And then we want to figure out when this guy will be equal to 0. Setting this equal to 0 and then solving for x, we'll get x is equal to 20. And we find that this is our critical number. Right? So what we're going to do is evaluate our function at this critical number and then at these endpoints and see which one produces a maximum value. So evaluating this at our critical number here, we're going to get 800. All right. Then evaluating our function at 0, we're going to plug 0 in for our x value, so we just get 0 here. And lastly, we're going to evaluate our function at 40. So we'll get 0 in this case as well. So this tells us that our maximum area will occur when x is 20 feet and will be 800 feet. All right, and so we found the maximum area, but referring back to the question, it did ask to find the dimensions and the area of the largest garden that can be enclosed with this much. So we need to find the dimensions. We already know that the maximum area occurs when x is equal to 20, so that's one of our dimensions, and so we need to find y. We saw that y was equal to 80 minus 2x. And so plugging in our x value, we're going to get 40. So the dimensions to maximize this rectangular garden with just $320 is going to be 20 feet by 40 feet. All right. So after seeing those two problems, this brings us to our little procedure and or strategy for solving optimization problems. So the first thing we want to do is introduce the variables and look for relationships among the variables. So we saw that in the last several examples. Then we want to construct a mathematical model of this form here, where we want to maximize a function on some interval. Then we're going to find the critical numbers of our functions, and then use the procedures that we saw in the last section to find the absolute maximum or minimum, and the values where this happens. Okay. And then we want to make sure that whatever solution we found in step 3 actually answers all the questions in the problem. All right. So let's do another example here. Now we want to maximize our perimeter. So in referring to the last example, the homeowner judges that an area of this much square feet for the garden is going to be too small and decides to increase this area to 1,250 square feet. We want to figure out what the minimum cost to build this fence would be and what the dimensions of the garden would be. And we're assuming that the cost of the fencing remains unchanged, so we're using the same function we saw in the last example. Okay, so this is still, I'm going to copy this, going to be our diagram. And the cost is going to be given by 8x plus 4y. Okay, and so in this case, what we want to do is minimize our cost, minimize c here. So our problem is to minimize our cost, subject to the fact that we want the area to be this much square feet. All right. Now something to note here is that both x and y must be greater than 0, right? For the same reasoning that we saw in the last example, we can't have a negative length or width, and these guys can't be equal to 0 because we know that when we multiply them together, we need to get this area. Okay. So again, our first step is going to be to rewrite what we want to minimize with a single variable. And we're going to do this using the fact that our area must be equal to this. So what we can do is solve for y, and we can easily do that just by dividing by x on both sides. So this tells us y is equal to 1,250 over x. So then we can rewrite our function in terms of just one variable x as this here. All right, so our problem is to minimize this for values of x greater than 0, right? And so we aren't looking at a function over a closed interval in this case, so we're going to be using the second derivative test. To do so, first we need to find the first derivative. First, let's simplify our function a little bit. This is going to be equal to 8x plus 5,000 over x. Okay. So then what we can do is rewrite this as 8x plus 5,000 times x to the minus 1, and so it'll be a little bit simpler to take the derivative. So we end up with 8x minus, because we bring that negative 1 down, 5,000 times x to the minus 2. Okay. And so this is equal to 8 minus 5,000 over x squared. Now we want to figure out when this guy is going to be equal to 0. So the first thing we'll do is add this term to the other side. So we get 8 is equal to 5,000 over x squared. Then we'll multiply x squared to both sides and then divide by 8. Okay. So we'll get 8x squared is equal to 5,000, and then dividing by 8, we get x squared is equal to 625. All right, and then solving for x completely, so taking the square root on both sides, we get that x is equal to plus or minus 25. But remember, we said that x had to be greater than 0. so x has to be positive. So this tells us that negative 25 is not in our domain. So 25 is our only critical number. So like I said, we're going to want to use the second derivative to determine the behavior of our function at this critical number. So we'll take the second derivative. We can do so rewriting our derivative as this here. So again, it's just a little bit easier to take the derivative using power rule. So this negative 2 is going to come down in front, so we'll get positive 10,000 times x to the minus 2 minus 1, so x to the minus 3. So we get positive 10,000 times x to the minus 3. And this is the same as this should be 10,000 here. And so that's the same as that, just writing this with our positive exponents here. All right. And so we want to evaluate this guy at our critical number here. And so plugging this in, we're going to get, we know that we're going to get a positive number. All right. So this, by the second derivative test, this tells us we're going to have a local minimum at x is equal to 25. And since this is the only critical number, we know that it's going to be our absolute minimum. So all right. So we're going to evaluate our function at that point here to determine what the lowest cost is going to be. This is going to be 200 plus 200. All right, so this tells us that our minimum cost is going to be $400. All right, and then going back to the question, so we found the minimum cost, and we also want to find the dimensions of this garden. Okay, so what dimensions will minimize this cost? So we know that we're going to have a minimum value at x is equal to 25, so we just need to find what our y is going to be equal to. We know that y is equal to 1250 over x, so just plugging in our x value. We get that our y is equal to 50. So this tells us the minimum cost to enclose a garden that is 1250 square feet is $400, and the dimensions of that garden are 25 feet by 50 feet. Now the last example we're going to look at is one where we want to maximize revenue. So we're told that an office supply company sells X permanent markers per year at P dollars per marker. The price demand equation for these markers is given by this here, and we want to figure out what price should the company charge for the markers to maximize revenue. Okay, so we're looking to maximize revenue, and then we want to figure out what is this maximum revenue. All right, so first, we know that our revenue is going to be given by our price times our demand, right? And then we're given this price equation here. So that's going to be our price times our demand. And so our demand is just going to be X. because X represents the amount of permanent markers. So multiplying this guy, we'll get our revenue equation. So that'll be 10x minus 0.01 x squared. Right? And then something to note here is that both price and demand can't be negative, right? So this tells us that x has to be greater than or equal to 0. And then since x has to be greater than or equal to 0, this implies that our price equation also has to be greater than or equal to 0. And then with this information, we can determine that x then has to be less than or equal to 10,000. So, similarly to the second example we looked at, our problem becomes that we want to maximize our revenue. So this is going to be our revenue equation. Over this interval here. All right. And we know that our function is going to be continuous on this interval. Since this is a polynomial. So we'll do the same thing that we did in the second example. We know that if the maximum exists, it'll occur at a critical number or at an endpoint. So we'll evaluate our function at either the critical numbers and the endpoints. So first thing is we'll find critical numbers. So we want to figure out when the derivative is equal to 0. The derivative is going to be given by this here, just doing power rule. And then we want to figure out when this will be equal to 0. So solving for x, we get that x is going to be equal to 5,000. Okay? So this is going to be our critical number. All right. Now we're going to evaluate. We're going to evaluate our revenue at the critical numbers and at our endpoints. So plugging our critical number into our revenue function, we get 50,000 minus 25,000, which is just going to be 25,000. Okay. And then evaluating our revenue at the first endpoint, 0, we're just going to get 0, so we're just going to plug in 0 for our x values. And then evaluating it at our last endpoint, let's write that a little nicer, we'll also get 0. Okay. So this tells us that our maximum value is going to occur when x is equal to 5,000. So when we have 5,000 markers, and it'll be $25,000 in revenue. We also want to figure out what price the company should charge for the markers to maximize this revenue. And we know that the price demand function was given in the beginning. And so what we want to do is just plug in this x value into our price function. Okay. And then we'll get 5. All right, so what we can imply from this is that when demand is 5,000 permanent markers, the price of a marker will be $5. And that the company has a maximum revenue of $25,000 when the price of a marker is $5. Okay, so that's what we can conclude here. I'll move that guy up. And then what price and what is the maximum revenue? So we answered all the questions there. And then something that I just wanted to note here. Oh, I didn't write it. That's okay. We can also use the second derivative test. We can take the second derivative of our revenue, and we'll find that that's just going to be equal to this here. And this will always be negative. Okay? So we know we'll have a minimum value at the critical number. Okay? And so this is actually how this problem was solved in the book. So if you want to take a look at that. And there are also a bunch of examples on maximizing profit and revenue in this chapter as well that I recommend you take a look at.